Okay, so last time we talked about simple roots, and that we proved that they form actually a basis of the Euclidean space where our root system is. So today we'll introduce another important notion, which is called the Weyl chamber, or Weyl chambers. By definition, a Weyl chamber is a connected component of the following set. It's we take E and we throw away all hyperplanes orthogonal to roots. So alpha goes over root and L alpha. Okay. So L alpha are hyperplanes orthogonal to roots, and we throw them away, look at what's left, and each connected component we call a Weyl chamber. Okay. There is more explicit description of Weyl chambers. So we can actually fix a polarization. So fix a polarization. So remember, polarization is a disjoint union of the root system into two halves. One half we call positive roots, and another half we call negative roots. For any map from R plus, let's call this map epsilon, from R plus to the set consisting of two elements, 0 and 1. We can introduce, so denote the following subset of E. C epsilon, it is all elements lambda in E, such that I would like to compute the inner product of lambda with alpha. This should be greater than 0, but with some sign, so greater or less. And this sign depends on the choice of epsilon, so epsilon of alpha. So alpha should be the positive root here. Okay, so anyway, so I'm writing an expression. So lambda, I take in some lambda such that if I can compute an inner product with positive roots, it's either positive or negative. So I have a choice, right? And epsilon is responsible for this choice, right? Notice two things. That first of all, C epsilon is connected.
Wait, for the definition of C epsilon, there is a for alpha, for any alpha or for?
For positive.
I mean for all alpha from positive.
Yes. Yes. Thank you.
So you divide the positive roots again into two halves?
Not really. I'm just for each positive root, I'm checking my element if it gives inner product positive or negative with this positive root. right? This information is enough only for positive roots. Of course, if I take negative of this root, then my inequality signs will just change to the opposite, right? So for this information, I really need just positive roots. So that's I took only this. So C epsilon is connected. This is because it's just a convex set, right? So this is just something that lives between bunch of hyperpoints. All right. So I should be more accurate here. I should say C epsilon is either empty or connected. I don't know was the our convention on empty set, if it's connected or whatever. So for empty set, nothing to check. But if it's not empty, if you take 2 points and just connect it with straight line, you can check that this straight line will lie inside such a thing. And moreover, the whole so this thing, maybe we can call it E tilde, is union over all epsilons of C epsilons. And moreover, it's a disjoint actually union, right? So it's just if you take some element, any element from here, it will give me some signs like that, right? Just it's either positive or negative when I compute this inner product. So everything in here belongs to some C epsilon. That's what I'm saying. Right? But these two observations mean actually that C epsilons is either empty or connected component of E tilde. And moreover, each Weyl chamber is of the form C epsilon, right? And each Weyl chamber is of the form C epsilon. Let me actually, just to make this statement more clear, I said it in words, but let me change it to disjoint union, right? So if you have a bunch of connected things and disjoint union of them gives you the whole space, of course, these connected things are connected components of this E tilde. All right, so this is some elementary geometry, Euclidean geometry. So. Right, so among all these Weyl chambers, or C epsilons, we have, when we fix a polarization, we have a distinguished one. Yes?
Different C epsilon intersection with each other?
They don't. So it just for some, it means that for some root, you have, you can, this cannot be positive and negative in the same way, so they don't. So this is why it's disjoint union. Of course, I throw in a bunch of empty stuff in here, but it doesn't really change things. So let me denote C plus to be C epsilon corresponding to all zeros So each positive maps to 0, so I have pluses here. Right? C plus is lambda in E such that lambda with alpha greater than 0 for any alpha from R plus. Then observe that C plus is a Weyl chamber. So according so let me, C plus is a Weyl chamber. So according to what we said here, we just need to check that it's not empty, right? But why is this not empty? Remember what was the polarization? So R plus was all roots. So we should have some regular element that divides R into R plus and R minus. So let me take this element. So let T in E be such that R plus is defined by the following. It's all alpha in R such that alpha with T is greater than 0. So let T be a regular element defining a polarization for me that I fixed. Then it belongs to C plus for trivial reasons, right? Just from what's written. So therefore C plus is not empty. So therefore it's a Weyl chamber. So this was my justification why I'm saying that C plus is a Weyl chamber, right? So I'm saying that because C plus is not empty, and it's not empty because defining element for R plus lives in C plus. So let us call C plus to be so C plus is called the positive Weyl chamber. Okay, so now I would like to consider some map from polarization to Weyl chambers. Natural map, right? So if I have polarization, then I have positive Weyl chamber. This will be my map. So I claim that this map is actually a bijection. So proposition the map, which one? So let's call it phi, from the set of polarizations to the set of Weyl chambers. So I take polarization corresponding positive roots and send it to the positive Weyl chamber. So of course, if I take some other polarization, my C plus will be different, right? So this is some map. Yes, so the proposition says that this map is a bijection. Let us prove that.
Sorry. How we can see that C epsilon is connected?
Yes, so I claim that if you just take, suppose it's not empty.
No, it's connected.
Yes, so it's either empty or connected. Okay, so suppose it's not empty. Therefore, I can find, and suppose I can find two elements, T1 and T2 in C epsilon. Then I would like to draw a straight line from T1 to T2. So I claim that this straight line is inside C epsilon. It's just because if you take a hyperplane and consider 2 points on one side of this hyperplane and connect it with the line, the whole line will be on one side of hyperplane. Now you have a bunch of hyperplanes. Like you just combine what I said. Okay? You can write formulas if you wish. Like just use this and write formula for a line and check it. But I don't want to do this, but I think what I said should be clear. Okay? Yes?
Yeah, okay. It's just that it doesn't seem clear to me.
Mm-hmm.
How can I imagine this C plus, C epsilon
Mm-hmm.
with, for example, with SL3?
Yes, very good. Let us draw.
Okay, what is C plus?
Yes. Okay. This is a good. Let us always think about A2, for example, right? So SL3. Let us draw what is the positive Weyl chamber and what are Weyl chambers there. Okay. Let me.
I don't understand.
Yes. Thinking about examples is always good. Yes. So in A2, you have the following roots. And then you draw hyperplanes orthogonal to this root. This one, this is orthogonal to this root. And this one, and this one. So everything so for example, this cone here is a Weyl chamber. This is another Weyl chamber. This is another one. Okay. What about C+? We need to choose polarization. So for example, we can choose these three to be positive ones. And then these two are simples. So this is usually a standard picture, standard choice. Right? So then the positive Weyl chamber, so I need to take this L alpha, right? Everything. So I just need to check that a point that I take is inner product with simple roots, positive. With simple roots is positive. Okay. So therefore, I take this subset, and what is positive taking inner product with alpha 2 is this. Right. So therefore, this thing here is C+. So it's an intersection of this one and this one. So I have two conditions, that alpha 1 with C is greater than 0 and alpha 2 with C is greater than 0. Right? So this is C+ for me. All right. And for example, this one, this is C. What? Yes. So C, whatever, C1, right? So let's see what are conditions for this one. So C1 Yeah, so of course I need a third root, right? So let me actually write it. Alpha 1 plus alpha 2 is the third root, but to check for C+, I need just this 2 because these are simple. This is not true for others. For C+, it works like that. So let me still add this condition, okay? For C1, I have what? So I have alpha 1 t less than 0, right? Then alpha 2 t is greater than 0. And then another condition that I have is with alpha 1 plus alpha 2, t is greater than 0. Yeah, so here epsilon was epsilon of alpha 1 and of alpha 2 and alpha 3 is 0. Here epsilon of alpha 2 and alpha 3 is still 0, but of alpha 1 is 1, right? Okay, so let's prove the proposition. Is it clear? No? Okay. Okay, so proof of proposition. Right, so what do we need to prove? We need to prove that it's bijection. Let's first prove that it's surjective, this map. So phi is surjective. So let me take some Weyl chamber, C+, or whatever. So take a Weyl chamber. I don't. So Weyl chambers, they are defined without fixing polarization, right? I'm just saying I'm throwing away all hyperplanes. So I don't know yet if it's positive or not. So I would like to see that there is some polarization, that for this polarization it's positive. So I'm proving surjectivity of phi. Okay. Take a Weyl chamber, some C. And then take, so it's not empty, therefore I can take some element in there. And it's in each element of Weyl chambers, they are regular, right? Because they are not zero with, inner product of them is not zero with any root, right? So therefore it's regular. On the other hand, and let me define polarization like this. Positive roots are exactly those roots that if I compute inner product with t from this C is greater than 0. Well, it's just some simple thing, but still. Then phi of R plus is C. Okay, then I claim that phi of R plus, actually this map is also can be defined like this. So you take our polarization, right? And you take some defining regular element for this polarization. Then corresponding Weyl chamber will be the one, the unique Weyl chamber that contains this regular element. Okay, so this is how this map works. It's just saying how we constructed C+ in different words. So this is connected component of E tilde containing T. So this is exactly our C. So surjectivity is proved. Then phi, how to prove that phi is injective? Also, pretty simple. So suppose I have two polarizations, so phi of R plus is the same as phi of some other polarization R plus tilde. And this is some C plus, whatever. Okay. Then, so I take some regular element. So I take some regular element from C plus, right? Then R plus, for example, is again. Then this T is defining element for R plus and for R plus tilde, both. For example, R plus is written like this. It's alpha in R such that alpha T right. So suppose that right. Right. So for R plus, I have some regular element that defines it. Right. So for some T1. Yeah, this I don't know yet, right? What I know is that, okay, I know everything. It's all pretty simple, but still, you need some to say something here, right? So R plus is some polarization, right? It's defined by some element T1, right? I mean greater than 0 for all. Just like that, right? On the other hand, if I take T from C plus, right, then C plus is defined by R plus as follows: that these are all elements, right? Remember, these are all elements such that T with alpha from R plus is greater than 0. Right? So just by definition of C plus from R plus, we have T with alpha is greater than 0 for all alpha from R plus and from R plus tilde as well. So suppose R plus is given by some defining element T1, right? Then we have that R plus right? R plus is inside. Maybe I even don't need this, right? So this line says that R plus is inside the following set: alpha in T, alpha in R, such that alpha with T is greater than 0. Right? So this line implies this, right? But on the other hand, so I have so what is the size of R plus? It's exactly R over so the size of root system over 2, right? So I have positive and negative. They just it's like that, but also the size of this set, right? So call this set, I don't know, A. The size of A is also, of course, R over 2. Because you have alpha and negative alpha inside, and so this exactly gives me the half of roots there. So one is inside another, sizes are the same, right? So therefore R plus is exactly this, right? And the same can be said about R plus tilde. So both R plus is this set A, and similarly R plus tilde is the set A, so therefore R plus is R plus tilde. So injectivity is proved. Okay, very well. So I would like, next thing that I would like to understand is that how the Weyl chambers are related to the Weyl group. Okay, proposition. If C is a Weyl chamber, then WC, so if I act by some element of Weyl group on C, is also a Weyl chamber for all W in the Weyl group W. So the Weyl group acts on the set of Weyl chambers. That's what this proposition is saying. Proof is elementary. So W. Yes. So it is defined as a something composed of reflections on E, right? So it's defined by its action on E, right? So these are elements of E, right? So W. If I take some V from E, right, then V to WV is of course a continuous map. Right, so therefore connected component goes to connected component. Right. But connected component of E tilde goes to connected component of the image of E tilde. So the only thing that we need to check that E tilde and the image of the tilde are the same things. Right? So then we are done. But for that, we just need to check that if I take union of hyperplanes, L alpha, and apply W to it, right? It will still be union of hyperplanes. This is just because the root system is closed under the action of the Weyl group, right? And therefore, the hyperplane goes to some other hyperplane. So each element of Weyl group is just a permutation of these hyperplanes, right? So therefore, W of E tilde is again E tilde, right? So connected component of E tilde goes to connected component of E tilde. So therefore, Weyl chamber goes to Weyl chamber under the action of W, and we are done. So we would like to see now that this action is actually transitive. Okay, so every Weyl chamber can be connected to some other Weyl chamber by the action of Weyl group. A proposition. action of W on the set of Weyl chambers is transitive. Okay, let's prove this. Right, to prove this, we need to introduce more terminology. In particular, we would like to introduce what is a wall and what is a face of a Weyl chamber. Wall, so right, so L alpha, this hyperplane, is called a wall of some Weyl chamber C. Okay, it's easier to imagine than to say it. All right, so if first of all, if an intersection of L alpha and C, I should say closure of this of C, right? Because C do not intersect with L alpha. So if this intersection is something of dimension, the same dimension as L alpha, right? This still works, so I should say it. It contains an open subset of L alpha. So this something is, I don't know, this is some, you know, well, it is manifold, maybe with corners and something. But anyways, I would like to say to put it in words like that. Also, what is so this intersection is itself. So if L alpha is a wall of C, then this intersection is called a face of C. Then C, closure of C intersect L alpha is called a wall of C. Okay, so just for you to can imagine what's going on again in A2, so example, in A2, what's going on? Suppose you have this is L alpha 1, right? This is L alpha 2. Right, this is alpha 1, this is alpha 2. So L alpha 1 and L alpha 2 are walls of C+, right? So wall of C+, and this is wall of C+. But L alpha 3, which is this one, is not a wall of C+, right? It just touches it at the origin. On the other hand, what is a face? So face of C++ is, of course, so this thing, right? This is one face, and this is another. Okay. Right, so we introduced this, and also let us introduce the notion of adjacent Weyl chambers. So Weyl chambers C1 and C2 are called adjacent if they have a common face. If they share a face. So these two Weyl chambers are adjacent, and these two are adjacent. Okay, the next observation that I will need is that if I have two different Weyl chambers, I have a sequence of Weyl chambers such that sequence of adjacent Weyl chambers connecting them, in a sense. So let me put exact statement on the board. Okay, claim. So let it be claim 1. So for any Weyl chambers C1 and C2, there exists a sequence of Weyl chambers. So the first element of this sequence is let us not have it C and C prime. So the first element of this sequence, the zeroth, is C. Then you have C1, C2, and so on. And the last element is, I don't know, CK, which is C prime.
So sorry.
Mm-hmm.
I think you defined two since two wall. Here there is a wall.
Yeah, so what's, yeah.
You mean that one you want to write face? Then something is called wall of C.
Yeah, so wall is the whole thing.
I mean, maybe you want to say here face?
Right.
Because in the beginning of the proof, you give a definition of wall, and these two are different. In the beginning of the proof.
Yeah, so in the beginning of proof, so I have three definitions of wall.
Means the words you write is not correct. This is not a wall.
It should be
Just write write.
So okay, so which one? I claim about walls. I claim that L alpha 1 is a wall of C++. Is that correct? Okay, and L alpha 2 is also a wall of C++.
Yes, but this intersection is not some L.
No, okay, about walls, no mistake, right? Okay, so I claim that C++ has two walls, L alpha 1 and L alpha 2. Okay, now faces. I claim that face in this case is a half of wall. Okay, so this is a face of C++.
I mean, the graph is totally correct, and the words about the graph. The sentence above.
Then something is called a wall.
Okay, so okay, let me inspect the wording. Suppose I have a wall, right? Then I take this intersection, right? And this is it's called a face. Yeah. Okay. Sometimes I just don't see what I'm writing. Mm-hmm. Okay, thank you. Yes, so statement is like that. So if I have two Weyl chambers, C and C prime, then I have a whole sequence of Weyl chambers. in this sequence, the 0th element is C, the last element is C prime, and such that C I is adjacent to C I plus 1. Okay, let's prove this. Let me take one element in C and call it denoted T. And T prime, let be element in C prime. All right. Then I would like to consider a path from T to T prime. So let gamma be a path from T to T prime. But I would like this path to be generic. So it does not intersect, so it intersects hyperplanes, but not in the points or lines of intersection of this hyperplane with some other hyperplane. Okay, let me put this on the board. Such that if I have some point of my path belongs to L alpha, then this point does not belong to any other hyperplane. So if I intersect a hyperplane, it is not a point of intersection of gamma with some other hyperplane. And we'll see on A2 what it means. So L beta for any alpha beta not equal to plus or minus alpha. So what it means in pictures, and why I can choose such a path. So in pictures, what I'm doing, again, our favorite example is A2. And suppose my C and C prime are C plus and the negative of C plus. So I choose 2 points, T and T prime. Okay. Then I just join them by, let me first try to join them by straight line. Okay. And suppose it happened that this straight line actually goes through this point. This is the path that I don't like, right? Because it intersects, say, this is L alpha 1, right? If it intersects L alpha 1 and L alpha 2, right? So suppose it's not on L alpha 2, right? Somewhere like this. At the same point, right? I don't want this, okay? So I would like it to intersect at L alpha 1, not at the point where L alpha 1 intersects with L alpha 2. So I actually can deform this path to go around this bad point like this. And this is the path, the gamma that I like, okay? So the thing is that if you chose some path, right, and for some reason you end up intersecting your L alpha at some point where it also intersects L beta, then you can deform your path a little bit to get out of the situation. Okay? This is just because each intersection is of codimension of codimension 2, right? So in other words, if you throw away union of all intersections of these hyperplanes, you will get something connected. Because if you throw away from E something of codimension 2 or bigger, then it is connected. So you can draw a path inside. Or you can just say, okay, draw any path, and then you can deform it like that. Anyways, so it just means that this path goes it goes like that. It just goes inside some Weyl chamber, and then it goes to adjacent Weyl chamber. When it goes outside of Weyl chamber, it goes to adjacent Weyl chamber. Okay, there's no way it goes to some other. So therefore, so take C0, C1, and so on, Ck to be the set of Weyl chambers such that gamma intersects them in the corresponding order. Right? And this will be exactly the sequence that we seek in this claim 1. Okay, so claim 1, I assume that I explained. So if any questions, still.
When you choose a path
Yes.
from T to T prime,
Yes.
you see the path is in L. Alpha is the.
Now, suppose that some gamma of S, so S is a parameter. So this is some point. Yes. So for some S in R. Here. Okay. So claim is proved, and I will need another claim, claim 2. Suppose that C and C prime are two Weyl chambers which are adjacent with let us specify their common wall. So with a common wall, say L beta. Then C equals to reflection with respect to beta applied to C prime. Again, it's easy to see. Proof of claim 1, of claim 2. All right. So let me take C prime and consider its closure and apply S beta to this closure. So C prime has a wall L beta, right? So therefore, this L beta so therefore, if I but S beta also doesn't change L beta, right? So if I consider closure, right, I will have some subset in L beta, right, of L beta in this closure, which of dimension of L beta, right? So, and if I reflect to respect to L beta, this subset is still there. So therefore, this has so I should say C. So I should write like this: C prime intersect L beta is still a phase of this. So yes, what I said is that let me call this F beta, right? Or maybe just F, right? So F, and this let me call C1. Maybe, okay, let me maybe call C1 to be S beta of C prime, right? So since this is true, therefore F, and C1 is some other Weyl chamber, and F is a phase of C1, right? So what's going on is that, okay, I have C prime, right? And if I consider closure, I include the phase of that it shares with C. When I consider reflection with respect to beta, this phase is not changed. So therefore, it's also a phase of C1. So F is a phase of C1. Okay. So therefore, C1 and C, but also F is a phase of C, right? So therefore, C and right. So therefore, we have three Weyl chambers with a common phase: C, C prime, and C1. And we know that C prime is not equal to C1, right? There are only two Weyl chambers which share a phase, right? So therefore, we forced to say that C1 equals to C. And therefore, C is S beta of C prime. Okay, so now we use these two claims to prove the proposition. Proposition, if you remember, was the following: that while a group acts transitively on the set of Weyl chambers. So now from claim 1 and claim 2, it's kind of obvious, right? So by claim, so continued proof of proposition. So so by claim 1 and claim 2, if I take so if I take any two Weyl chambers, for any Weyl chambers C and C prime, okay, let me take the two Weyl chambers, find this sequence of adjacent, and then go from C0 to C1 by reflection with respect to beta that defines a common wall. Then from C1 to C2, again, by reflection that is defined by another common wall between C1 and C2, and so on, right? So therefore, we have C prime, right? Or, okay, we would like to Yes, so we would like to go like this. So C is S beta 1, S beta 2, S beta 3, and so on, S beta K of C prime. Maybe let me put prime here and change like this, right? B1, B2 here, sorry, and then beta K minus 1, beta K. So for some beta 1 and so on, beta K. So therefore, if we denote this to be W, right? So therefore, C prime is WC for some W from W, and therefore we're done. We proved proposition. So we connected two Weyl chambers by some element of Weyl group. All right, so we have corollary 1, which says that for any two choices of simple roots, so for any two sets, pi and pi prime of simple roots, we have, well, pi prime is just W of pi for some element of a Weyl group. So this is a very important statement because we would like to classify all root systems, right? And we would like to do that by classifying simple roots, possible sets of simple roots. And for us, it's important in which case two different choices of simple roots give me the same root system. And so this actually answers this question. So if I have one root system and two different sets corresponding to simple roots, then these two sets are related by an action of an element of Weyl group. Okay, so let's prove this. Okay, so choice of simple roots is the same as choice of polarization, right? So once we choose polarization, you have already simple roots, right? So let R plus and R plus prime be the polarizations corresponding to pi and pi prime, respectively. Right? Then let us take two different Weyl chambers, positive Weyl chambers. One corresponding to this polarization, and another to the primed polarization. Okay? So denote C to be, so remember our map phi. So phi of R plus, so it's positive Weyl chamber corresponding to, so maybe C plus even, to R plus, and C plus prime to be the positive Weyl chamber corresponding to R plus prime. Okay, then according to our proposition, we can find an element of Weyl group that connects this Weyl chamber with this Weyl chamber, right? So there exists, so by proposition, there exists some element W such that C plus prime is W of C plus. But then we have the following. So I claim that R plus prime is W of R plus. Why is that? You just need a couple of lines to see that. Indeed, so what should I take? So I take T in C plus, right? In the Weyl chamber corresponding to R plus. Then, of course, WT is in C plus prime, right? Then let me consider R plus prime. So this is by definition. So WT, since it's in C plus prime, it's a defining regular element of R plus. So R plus prime are all roots such that alpha with WT is greater than 0. But this set is the same as the following set. It's W alpha in R, right? So W alpha in R such that alpha in alpha with T is greater than 0. So this is just because W alpha, WT is the same as alpha T, right? W leaves inner product invariant. So in this set, we change alpha to W alpha, right? It still will run over all R's, right? And then we have this equality, but this is exactly W of R plus, right? Because without this W here, it's exactly the definition of R plus, because T is from C plus. So we have this. This is the proof of this statement. And finally, because this actually already means what we want. So therefore, P prime is W of P. This is just because W maps simple root to simple root. Right? Well, W is a linear map. Right? So if it was so if I took some root in here which was sum of 2, then it's sum of 2 here, and the other way around, right? So W is linear map, so therefore we have this. If I started with something which is not the sum of 2, then I end up with something which is not the sum of 2 there. Okay. So we're done with the proof of corollary. So next important thing that we need to discuss is simple reflections. So by definition, the reflection S alpha with corresponding to simple root is called simple. Okay, so we kind of answered the question for which two choices of simple roots I have the same root system, right? So now the question is, if we have a set of simple roots, can we recover root system? Okay, so that's our next question. And for that, it's important to have this because we have the following theorem. It consists of two parts. First part is that simple reflections generate W. So before W, by definition, W was something that is generated just by reflections, right? So the first part says that simple reflections are enough. Okay. And number two is that if I take pi and apply and consider all different roots that I can get applying the Weyl group, I will get the whole R. And second part actually answers to this question that how I can recover R from P. Like both of them. So if I have pi, right, then I have simple reflections already, right? But then if I have simple reflections, then the first part says that I have the whole Weyl group. But then going back to the second part, acting only by the whole Weyl group or by simple reflections, doesn't matter now, I get the whole R, right? Okay, so let's prove this. Let me actually list all the simple roots. So denote, so let pi be this alpha 1, alpha 2. So I have some number of them, and this number is actually dimension of E, right? It's also called the rank of root system, and I denote it by R small here. Right, and also let me denote S alpha E I by S just by Si. Okay, so let me now take some root alpha. And we would like to prove, so we want to see that S alpha is S I1, Si2, and so on, Sik for some integers I1, Ik, and they are from the set 1 all the way to R, right? So this is our goal, right? Because W is generated by all S alphas, and if S alphas are products of simple SIs, then we at least prove the second part, the first part there. All right. So let me, and again, we have, as an instrument, we have Weyl chambers. So let me take C to be the Weyl or a Weyl chamber containing I would rather say with a wall L alpha, right? Each L alpha is a wall of some Weyl chamber. So let me take a Weyl chamber such that L alpha is a wall of C. All right. And then let me connect it by a sequence of adjacent Weyl chambers as before with C+. right? So let so I have C0, which is C plus, and then C1, and so on. C and C, say, I don't know, L, to follow my notes, is C. Be a sequence, so be a sequence of adjacent Weyl chambers. And then let me also fix a wall, which is a common wall of Ci and Ci plus 1. All right, so let L beta I be the common wall of Ci and C I minus 1. This is just some notations of beta I is like that. Then actually we know just from the proof of the previous proposition, we know that C is S beta L, S beta 1, and S beta L minus 1, and so on. And up to S beta 1, right, applied to C plus. Right, so beta 1 is a common wall between C plus and C1, right? I apply S beta 1, I get to C1. Then I apply beta 2, I get to C2, and so on. And at the end, I am at CL, which is C. Very well. So I would like now to prove that this is actually a product of simple reflections. So how to do this? I just go step by step. So first step is to look at this reflection. So the walls of the positive Weyl chamber, what are the walls of positive Weyl chamber? So that's the question. Yes. What restricts? So they are L of with some roots, right? Yes, but these roots, so I claim that these roots are exactly simple roots. Remember, for example, the example with A2, right? The walls were L alpha 1 and L alpha 2. But this is the case for in general. So L alpha I from 1 to R. So therefore, beta 1 should be 1 of alpha I, right? So therefore, right, so I reflect with respect to some wall in C plus to get to adjacent, right? So therefore, beta 1 should be 1 plus or minus, actually. Alpha doesn't really matter if I choose plus or minus because reflection is the same and the hyperplane is the same. Alpha I1 for some I1. Okay, so then S beta 1 is S1, Si1, right? Of course. Okay, next step. Let me take, so here, then after that, we have S beta 2, right? So we have S beta 2, and let me denote this. So this is already denoted as C1, right? So what are walls of C1? So I should take walls of C plus, of C0, and apply S beta 1, which is the same as Si1, right? So walls, so let me continue maybe here. Walls of C1 are Si1 alpha j. So j is from 1 to r. But so it means that beta 2 should be of Si1 of alpha I2, right? Beta 2 should be 1, or again, plus or minus, of course. So beta 2 should give me a wall of C1. All right, but what it means? Then let me write down S beta, then S beta 2, what it is. So this is S, and then with respect to Si1 of alpha I2. But remember, if I take a reflection of with respect to some root and apply to this root some element of W, then I can write it like this: Si1, S alpha I2, Si1. Right? We had this proposition before that SW of alpha is W S alpha W inverse. So that's what I'm applying here. All right. But then, so therefore, this equals to what? Si1, Si2, Si1. So S beta 2 is like that. But then what is S beta 2, S beta 1? S beta 2, S beta 1. So S beta 2 is like this: Si1, Si2, Si1. And then S beta 1 is the same as Si1. So this is reflection 1, and so reflection square is 1, right? I reflect 2 times, I get nothing. Well, I'm at the same place. So therefore, this is Si1, Si2. And then you can continue in the same manner. You will always have some cancellations like this, right? And you actually continue like this, you get, so continue. And therefore you get that beta, I don't know, j is Si1, Si2, and so on, some j, right? Maybe minus 1. And then alpha ij. And the corresponding right, then we have S, right. So how to write this shorter? Well, the corresponding S beta sequence like this, S beta j as beta j minus 1 and so on to s beta 1, right? Just the same computation as here is just s I1, s I2, and so on, s ij. At the end, we will get, so this is some, if we denote this as w, right? So therefore, C is W C plus, where W is a product of simple reflections. But then remember, we started with the root alpha, right? And alpha was a wall of alpha was a wall of C, right? So therefore, we have that L alpha is W of L alpha I for some I from 1 to R, right? Because this is a wall of C, this is a wall of C plus. So therefore, each wall of C is a W applied to some wall of C plus. Okay, but this means that actually alpha is plus or minus W applied to alpha I. Right? Because, well, we had before that this is the same as L W alpha I. So this we saw in the last lecture. So therefore, if this hyperplane equals to this hyperplane, this means that alpha is plus minus W of alpha I. So therefore, we proved the first which part. So each root we can get just right. So yes, so each root we can get by applying simple reflections, right? Well, okay, so from this we actually can see what? That S alpha, again, we're applying this, right? Then S alpha is W Si W inverse, right? So this consists of simple reflections. This is a simple reflection, and this consists of simple reflections, right? So therefore, the part 2 is proved. So part 2 false. Okay, so now how to get part 1? Well, you by applying some simple reflections, you get plus or minus alpha, right? So part 1 says that any element of R can be given by applying elements of Weyl group to elements of pi, right? So this is an element of pi. And I apply elements of W, and I get plus or minus alpha, right? If I get minus alpha, then I apply reflection with respect to alpha, which is also an element of Weyl group, and get plus alpha, right? So therefore, if I call this star, so from star, I get part 1. And we are done. So now we know correspondence between set of simple roots and just root system. we can recover root system out of simple roots. And we know that if two sets of simple roots give me the same root system, they are related by an action of a Weyl group. Okay, so let us stop here. It's almost, I think it's actually everything that we need to know. Then next time we will have classification, relation to classification of semi-simple algebras. So we're almost done with technical stuff.